magnetic torque on a current loop. Let's do. I'm going to solve one sample problem, and then I think this is, you'll see that there's not that much to it. The whole process of grasping the concept, I think, initially in deriving the equation might be a little might seem at first a little convoluted, but the actual problems themselves are fairly straightforward. So you have the picture here. In the picture you have the magnetic field that is drawn. So this is the magnetic field B, and then you have the vector A. I'm going to put A here. Here's where I have A. All right, so there's A. If you're in algebra-based class, don't worry about what this mu means. If you're in calculus-based physics class, you will have to think about that mu, but for the moment, all we need is what's here in this picture. So we have the equation for the torque. Torque is just I A B sine, and I put theta over there. Just that's fine. Doesn't really matter, theta or alpha, as long as you remember that this is the angle between A and B. This is the angle between A and B, and in the picture here you have that shown, right? If this is A, I'm looking here. This is right. This is A vector. A vector is always at 90 degrees to the surface, right? So I could add this here. This is at 90 degrees to the surface. Theta is between A and B. So let's do number one. 20 centimeters squared loop with 3 amps. Through it is at 25 degrees with the magnetic field. What is the torque exerted on the loop? So what I have is the magnetic field B, which is 2 teslas. I'm going to write 2t. I have the area vector, which is 20 centimeters squared. We'll have to convert that to meters squared. We'll do that in a second. And I have the current I, which is 3 amps. 3 amps. And it's at 25 degrees. So let's see what it says. The loop is at 25 degrees with... It doesn't actually say clearly enough whether that 25 degrees is the actual theta or whether the 25 degrees, that's the angle between the surface of the loop and the magnetic field. So here's what I mean. The 25 degrees, we'll take the easy way out and we'll just say this is 25 degrees. But on the quiz, I would be more precise because this is not very clear. So this 25 degrees here, that could mean either the actual theta, so this angle here, between A and B. If that's the case, great, we're done. Or it could actually mean the angle between the magnetic field and the loop itself. So perhaps it's this angle. But we'll take, since it's unclear which it is, and we'll take the easy way out and we'll just say it's the actual theta and move on. So so let's convert 20 centimeters squared to meters squared. That's 20 centimeters times a centimeter, which is the same thing as 20 times a centimeter is 100, so 0.01 of a meter times 0.01 of a meter. And now you can see that what I have here is 10 to the minus, so this is 20 times 10 to the minus 4th meters squared. All right, so the unknown is the torque. What is the torque on the loop with that specific setup? Should I draw a picture? I want to draw a picture. I guess I do want to draw a picture. Let me draw a picture. So what I have is the current I that flows like this. Here's current I. My current flows out of the page, flows into the page, and then I have a magnetic field, and the magnetic field points like this. B. Maybe I'll put another one here. I'll put another one here, and the A vector points like this. A vector is always at 90 degrees here, but the angle theta is given to me here as 25 degrees. So this is the picture I have, and of course there's going to be a force acting on this thing, so there's going to be a force that points in this direction, force that points in this direction, therefore this thing will rotate, and I'm going to end up with some torque. And look at that, I wrote that torque is 0. That's not really the case. So the torque is the unknown. All right, well, let's go ahead and calculate this thing. So torque equals I times A times B times the sine of the angle theta. Just plug in the numbers. I is 3 amps, area is 20 times 10 to the negative fourth. Magnetic field is 2, and then sine of 25. Let's calculate this, see what we get. So I got 5.1 times 10 to the negative third, and units are Newton meters. Newton meters, and that's that. That's all there really is for calculating torque on a current loop in a magnetic field. So you should try to do the other problems on this worksheet and see how that works out. But this is it for the torque.